Today I have the honor to present to you my theme intituled Design of Patch Antenna based on Metamaterials CSRR cells for Telecommunication Application. Before starting, I will give you an overview of the work plan. I begin with introduction, design of planar antenna based on metamaterials, design and simulation of SRR and CSRR cells, interpretation of results before and after adaptation. The emergence of new technologies continues to spread as it develops. Telecommunications are among the technologies that have revolution of our way of life in the 20th century. From the telegraph to the internet, from the wireless to the cell phone, the progress made is spectacular. This new technology gives birth to a new 5th generation communication network, which presents itself as the evolution of telecommunication system but with a much greater capacity. The object of this work is the design and simulation of an antenna based on metamaterials in order to miniaturize the dimension of planar antennas. Metamaterials is artificial materials (DNG). Its goal is the miniaturization of structure, the reduction of the size and the weight of the structure, embedding antennas in 5th generation telecommunication system, designed and simulation by the three-dimension software CST using the find integrate method. Metamaterials is given with equation an. The first figure presents metamaterials made of the find wireless wire and the CSR introduced by the University of California. The first figure presents classification of metamaterials. Antenna patch design and simulation. The different elements of the patch are given above. The dielectric permittivity of substrate FR4 is equal 4.3. Thickness of the metallization copper H equal 0.035 millimeters. Height of the dielectric substrate HS equal 1.556 millimeters. Frequency FR equal 3.5 gigahertz. Adaptations to the 50 ohm and upper power supply by microstrip line. The table 1 gives dimension of patch antenna parameters. Design of a rectangular patch antenna with a notch. The figure 3 shows a rectangular patch antenna with a notch. The latter are used for a better adaptation of the antenna to the frequency resonant 3.5 GHz. Figure 3b gives the result of the simulation of reflection coefficient of the frequency 3.5 GHz. Figure 3c shows the radiation pattern of the antenna. Figure 3d represents the directivity of the antenna with a gain of 60.2 decibel, which shows that the antenna is directional. Design and simulation of SRR and CSRR cells. The figure 2 represents a reflection coefficient for frequency of 3.5 GHz and transmission for 3.14 GHz. The figure 4 represents of the unit of square cell SRR, and the dimension of the cell SRR are given in the table of table 2. The figure 5 represents and the dimension of 3 rings CSRR unit with 3 openings in the same direction and its as parameters. Interpretation of simulation results before adaptation. We have 6 antenna with different CSRR on the page. The different result of the coefficient reflection before adaptation is given in the figure 6. The different results are given under 3.5 gigahertz. The table 3 represents the result of coefficient as a frequency of a function of frequency for different CSRR cell on the patch antenna. Interpretation of simulation results after adaptation. The figure 7 give patch antenna after adaptation with CSRR cells and their coefficient reflection. The more coefficient are given in the frequency 3.5 GHz. The table 4 represent give result of the coefficient of reflection as a function of the frequency of different CSRR cells on the patch. Antenna radiation patch after adaptation. The figure 8 gives 3-dimensional radiation diagram and 2-dimensional polar diagram of the different patch antennas. Miniature and antenna performance. Table 5 shows the different patterns of the parameters of the patch antenna after adaptation, and Table 6 represents the miniaturization rate, efficiency, and the bandwidth of the different patch antennas. The best result of the antenna with the CSRR cells on the page is given in the antenna with 2 CSRR vertical. Frequency is equal 3.5 gigahertz. Miniaturization rate is equal 15.89%. Efficiency is equal to 2.98%, and the bandwidth is equal 0.16 16 decibels. This work allowed us to design a planar antennas based on metamaterials in order to study the influence of different parameters on the radiation pattern of rectangular multi-layer patch antenna for 5th generation application. The antennas designed and proposed as a reflection coefficient resonating at 3.5 generation gigahertz. This frequency is used for 5th generation application. Metamaterials make is possible to have characteristic beyond the nature of the behavior of the antennas. The goal of this work is to have miniaturization of patch antenna use to ring CSRR cells. Antenna miniaturization technology minimize cost and gain and workspace, hence saving metamaterials. The figure 7 give photograph of realization of the patch antenna based on metamaterials with 2 cells and 2 ring CSRR metamaterials patch on the patch antenna for 5th generation application design in the Tlemcen Telecommunication Laboratory. Thank you for your attention.